Okay. So we're live on YouTube. Welcome, Ben Bridgens. Ben Bridgens is professor of regenerative architecture in the School of Architecture, Planning and Landscape at Newcastle University. He is also a founding member of the Hub for Biotechnology in the Built Environment, and he works at the interface of engineering, architecture, and design. Critically examine sustainable technologies and exploring the potential for combining traditional construction practices with biotechnology and natural systems. He goes beyond just sustainability and he wants to create a regenerative built environment. Ben's work is driven by a question. The question is, can we move beyond sustainability and create a built environment which has positive impacts that is beneficial and enriching to the natural environment? He wants an environment that does not degrade, but performs better as it ages. And the environment should also be a pleasure to construct and to be delightful to inhabit. This question was actually the reason why we invited Ben for this year's talk in the module Emerging Fields in Architecture, as those questions relate very much to our focus and our journey as we are asking for the essential in our module Emerging Fields in Architecture. So first of all, Ben, thank you very much for coming. Today we have a hybrid meeting, meaning that we are sitting here in the lecture hall with some of the students, some at home, and you were in the OK. So later when we discuss, I will turn the computer so you will see all the students. Or before we start, can I ask you to turn either on your camera and I turn around the computer so you see the setting of our... You still like coming and going, but welcome, Ben, and we're looking forward to your talk.
Thank you very much. Thank you for the introduction and thank you for inviting me. I'll just work this out. I'll just, whoops, just share my screen. Move things around and get started. Get rid of that. I'll move this thing. Right. Is that working? You can just see the slide and...
Yes, you can see the slide.
Great. Okay, so good morning. Thanks again for the introduction. So my talk is titled Regenerative Architecture, but I've got a question mark at the end because it's a really challenging area, and I don't want you to think that I'm just going to sort of tell you, how to do regenerative architecture and how to make the world a better place, because it's a very difficult topic that I'm starting to explore and, trying to show you some ideas and options, but it's really just the start of a long journey. So to get started, these slides will move. To get started, I wanted to tell you a little bit about myself and my background, because that sort of explains why I'm talking about this and where I've got to. So my background originally, I'm not trained as an architect. I'm trained as an engineer, a structural engineer. So this is some images from the early days of my career, designing bridges, designing buildings, specializing in lightweight structures, and also in sculptures, in working with artists to make large pieces of public art stand up. So really exciting, interesting pieces of structural engineering, very challenging use of materials. But it didn't take long for me to start questioning what we were doing here and what we were using these materials for, particularly with the artworks. So making this interesting donut-shaped installation in a new public square made from stainless steel, sheets of stainless steel welded together and inflated to make these sort of curved pillows. Very interesting technical challenge, quite an impressive piece of artwork. But I started thinking more and more, what are we doing with these materials, these very harmful and damaging materials to extract and make stainless steel, is a very high energy damaging process. And then we make it into this sculpture in this square. And perhaps would it be better instead to plant trees to make this a green space, which would make the space cool and relaxing, and intercept rainwater and stop flooding. So I started having these questions in my mind about, the high tech and the modern materials, and actually using nature instead, and whether that could be a much more beneficial way of working. And that's really sort of followed through and influenced my work extensively through to today. So it's around then I left engineering practice and moved to the university, moved to the School of Engineering at Newcastle University, to give me the flexibility to think more about these questions and not be constrained by working on real projects. One of my research projects was about responsive materials. So this was using the responsive nature of wood, and the response of wood to moisture, and how wood shrinks and swells with changes in moisture content, and how you can use that to make responsive materials. So here we have thin layers of wood glued to a thin layer of glass fiber composite, and as the wood shrinks and expands with changes in moisture, we get these very elegant movements. And the idea was to try and make buildings that could respond to their environment without the need for sensors, electricity, computers, motors, and so on. Could we get away from all those high-tech systems and instead just use the properties of materials to create responsive facades? And so this moved on to another prototype here of a facade module. And the idea is when it's dry, we get light or ventilation, and then when it rains, just from the properties of the materials, the facade closes, becomes sealed to the rain, and then again as it dries, the facade opens up again, which was great fun, experimenting with these materials, and I think it was perhaps a step in the right direction. But actually, if you look at this critically from an environmental point of view and think about the materials, it's not really a very good strategy. We're taking wood and we're bonding it to fiberglass. We're making a composite material which can't be recycled. We're making something that's quite fragile. We did durability testing. We put these outside. I think they'll probably last for about 5 years. But then we have these composite materials, glass fiber and wood, which you can't recycle, you can't take apart. You'll just end up throwing them into landfill. So actually, as a long-term strategy, it's not very good. And there are ways to get around this. We could use just 2 layers of wood orientated differently, use a biodegradable resin, perhaps. So I think there is still potential here, but again, it made me think: Are we doing something wrong here by cutting the tree down, making thin layers of wood, and then trying to use them? And would it actually be better to use the tree directly? For example, if we want shading in the summer and not in the winter, we can plant trees, or we can have vines growing on the outside of the building and actually use the living organisms and the living plants functionally around and on our buildings, rather than trying to make our own sort of more complex systems, which are much more likely to fail and less likely to last as long. So that was kind of just a little bit about the background of how just a couple of examples of how I went from sort of engineering through to a much greater interest in the potential for living systems and living organisms to be used much more directly in the built environment. Then if we take a step back and think about what the problem is here that we're trying to solve, and I'm sure you're all familiar with this, so I'll just talk about it very quickly. So this was from a few years ago, 6 years ago, but it gives a good idea of the problem that we have with the built environment at the moment. So we have about 40% of global CO2 emissions are related to the built environment. So 28% building operation, 11% materials and construction. And because that building operation, the energy needed for heating, cooling, lighting, because that's so big, 28%, understandably, it's been the main focus of changes in construction and net zero, sort of move towards net zero construction, meaning net zero energy required during operation. So certainly in the UK, that's what we've been focusing on, building regulations changing, requiring ever greater levels of insulation and air tightness and so on to reduce this need for heating in cold climates, and changes in lighting technologies to reduce the energy needed for lighting. And that's all fantastic, that focus on operational energy. I think a lot less has been done about the 11% of global CO2 emissions caused by actual construction of buildings. And that's really my interest and my focus. And this 11% is becoming more and more significant as the operational energy is reduced. Then proportionally, the impact of the construction materials is becoming more and more. And it's not just about carbon dioxide emissions. There are a whole range of environmental impacts of making construction materials. There are architectural implications of the use of steel and concrete throughout the world, and also social and economic impacts of the global supply and trade of these materials. So just to give a couple of examples, again, I'm sure you're all familiar with this, but I think it's worth emphasizing. So cement and concrete, incredibly damaging materials. There are various different figures, but suggestions that cement accounts for between 5 and 8% of global CO2 emissions. This amazing statistic that concrete is the second most used substance on Earth after water. The quantities of concrete used are absolutely incredible. And the other material that's used extensively, of course, is steel. And I think a couple of important points to make about steel. And one is that, yes, it's very, very strong. It's ductile. It bends, so it can be used safely. But actually, if we sort of look at steel objectively, there are so many problems with it. And I think it's interesting that people get used to certain materials and sort of forget about the downsides and feel that those materials are incredibly good and necessary for construction. So steel, it's very strong, but of course the raw materials aren't available in most countries, so it has to be transported around the world. It has to be mined and processed, so we get environmental destruction, very high temperature processing. We need to use a lot of energy, very high CO2 emissions. It's very expensive because of this, the energy and the transport. It's incredibly heavy. I mean, it's a big problem with steel that the strength to weight ratio isn't actually very good because it's so heavy. It's very difficult to work with. It has to be shaped in a factory when it's hot. We can't work with it on site. It conducts heat and cold, so we have to be very careful about insulating around steel structures. It's actually very bad in fire. In a fire, steel loses its strength and starts to bend. If we put it outside, it rusts and degrades. And it can be recycled, but needs very high temperature processing. So it's actually amazing that steel is so popular. You know, imagine if we created another new material and it had all of those problems, I suspect people wouldn't be very keen to use it. So it's good to look objectively at these materials and actually realize they aren't as fantastic as people think. And that might make it easier for us to start using other materials if we really understand the limitations of these materials. And the other thing, I think it's very important to look beyond CO2 emissions. You know, that's just one measure of environmental impact. But this is an example of the impact of us using steel in construction. This was in Brazil, 2019, where an iron ore tailings pond, so that's where they keep the toxic waste that's produced when processing iron ore, and the dam collapsed, and this wave of toxic red mud moved down this valley, killing a large number of people and completely destroying the villages and ecosystems along this valley. And this is a regular occurrence. I've seen this happen several times over the last couple of decades. So it's really important to not just think in terms of CO2, which everyone likes to, because it's a number that you can easily measure and compare and offset, but you can't offset this kind of tragedy that results from the materials we use. And there are other perhaps less important, but I think still significant issues with using the same materials globally. We end up with this globalized commercial architecture of steel, concrete, glass. One of these buildings is in Poland, one's in America, but of course they look exactly the same. So it's just another reason why perhaps we should be thinking about materials which are locally available, locally made, to start to return to some kind of distinctive local architecture. And then I just wanted to look at a couple of examples of sort of best practice now, because it would be easy to think that architecture and construction is moving towards much lower environmental impact construction, which is true to an extent. So this is an example from the UK a few years ago of passive housing development, so very low energy building, very highly insulated, very good air tightness, very high performance buildings that will need very, very small amounts of energy to run. But if we look at the materials, things aren't so good. We've got bricks where we had to dig up the clay, we had to heat the clay to make the bricks. The bricks are joined with cement mortar. We've got sheet metal. See the zinc cladding there. We've got sheet metal with all the impacts of metal extraction. We've got concrete foundations. We've probably got plasterboard linings on the inside of the walls, again made with cement and impossible to reuse if there are any changes to the building. So from a material point of view, these sort of state-of-the-art developments still have a lot of problems. The same is true of sort of best practice construction, timber frame construction, exactly the same issues. Plasterboard, cement-based plasterboard, concrete foundations, carpets used for flooring, which often can't be recycled and use oil-based materials. And then even when we look at what we might think of as the sort of very best practice, using big slabs of cross-laminated timber, which I think is a very good move. We're moving away from steel and concrete structures. We're using wood to form both structurally and to form the walls of the building. We're storing carbon dioxide within those big slabs of wood. But again, there are still issues. We've got adhesives that are used to bond pieces of wood together to make the cross-laminated timber. We've got transportation. We've got the forests that are grown to grow that wood, which are not natural forests. They're monoculture forests with just all the same tree, very limited biodiversity. We've still got concrete foundations. We've still got some cladding on the outside of the building. These slabs of cross-laminated timber aren't suitable as the exterior of the building. They're not durable enough, so the building will be covered in, certainly in the UK, normally in bricks, to make it look like a proper brick building, because timber buildings aren't very popular in the UK, or it might be covered in sheet metal or hopefully timber cladding. And there might still be plasterboard and oil-based insulation materials and so on. So it's a step in the right direction, but there's still a lot of limitations. And then the way I see the construction industry going, I find more worrying, I think. So one thing that the construction industry is doing to try and improve and become more efficient is use off-site fabrication, so making larger and larger components of buildings in factories, but again, often with very little thought about what the materials are. So still using the same very damaging materials, but just constructing them in a different way that's more efficient, which seems like a wasted opportunity. And then what I find particularly concerning, the great interest in 3D printing. It's really exciting fabrication method, with, of course, all sorts of interesting architectural possibilities, giving amazing control of the form through large-scale 3D printing. But of course, one of the easiest materials to 3D print with is concrete or other cement-based pastes. So this project, world's first 3D printed concrete housing project to be built in the Netherlands, and then the description of the project said this process addresses the environmental impact of construction with the reduction in cement resulting in a decrease in CO2 emissions, which I think is completely misleading. What they're talking about is the fact that with 3D printing, we can leave these voids in the wall. We don't need to use solid concrete. But of course, no one in the Netherlands or very few people in Europe would be building with solid concrete walls. Sort of standard practice is much more likely to be a timber frame construction now. So I think this argument that 3D printing sort of reduces cement use, but actually it's encouraging the use of cement and concrete, which is completely moving in the wrong direction. So that was my sort of being critical about the about sort of modern construction. And of course, what lies behind all of this is this idea of sustainability, which has been around for a long time, really since 1987, when this definition of sustainable development was written, about sustainable development meeting the needs of the present without compromising the ability of future generations to meet their own needs. But unfortunately, in the decades since then, I think that idea of sustainability has been sort of watered down, and the general approach to sustainability tends to be very small incremental steps. So, very small reductions in, for example, reducing the cement content of concrete. So you make these small incremental changes, but at the same time, with economic growth and population growth, the overall impact of an industry often keeps going up, even with these small incremental improvements. And I've spent a lot of time trying to think about whether anything that we build is actually sustainable, because so many people talk about sustainable construction and new sustainable buildings, but really taking this definition and thinking, are we building things which do not cause any harm to future generations, that we could keep building like this for hundreds or thousands of years? And then we start to find that actually current construction methods don't stand up to that kind of criticism. And one of the only examples that I've managed to find was actually looking back to very, very simple construction, Roman construction, using local materials, local stone, with no mortar to join the stones, just very carefully shaped stones that fit together, dry, which has lasted for about 2,000 years and is still in use. It's not used for the same purpose. It's not used to transport water, but it's still used as a bridge. So I think that's one approach to sustainability, is to try and make something incredibly durable so it can literally sustain. Of course, there are other approaches to sustainability, design for deconstruction, adaptable design, trying to design things that can change and adapt. But actually, it's incredibly difficult to do that without having negative environmental impacts every time you make changes. It's very, very difficult to make something that can be durable but flexible. But then the other question about sustainability is whether that's really enough. And given the catastrophic destruction of our natural environment in so many ways around the globe, perhaps we should be aiming to do more than just being sustainable and doing no more harm, not causing any more damage, and sort of trying to stop there. Perhaps what we should be doing is designing in a way that we start to repair the damage that we've done. And this is sometimes called restorative design and sometimes called regenerative design. And I started thinking about this some time ago when I read these books by McDonough and Braungart. You're probably familiar with these. Certainly Cradle to Cradle was a really influential book, which sort of started the whole idea of the circular economy and about designing for circularity, designing for true circularity. And McDonough and Braungart were very careful and critical, and they were thinking about circular cycles to make sure that things were really being recycled and not being downcycled, not losing value, not being used for sort of less good uses. For example, if you crush concrete and then use it as a sort of fill material under a road, it's not recycling, it's downcycling, because you've lost the value and quality of the material. So Cradle to Cradle was about having these truly sustainable cycles. But then their next book, The Upcycle, was about going beyond sustainability and actually trying to design for positive impacts. And I really like their phrase, designing for delight and abundance rather than sustainability and limits. So they saw sustainability as a very sort of limiting and negative concept, that we're just going to try to sort of do no harm. We're going to try to minimize everything we do. We're going to try and have a sort of as little activity as possible to minimize people's environmental footprint. But their argument in The Upcycle was that actually, if we can have positive impacts, then we don't need to limit people's activities. The more we do, the better, if we're actually having a positive impact. And so when I originally read that, it's a very, very exciting concept. Suddenly we can be doing good, we can be improving the world. The problem, of course, is how we actually do that. So this led to this question, which was in my introduction, about whether we can go beyond net zero and create buildings which have positive impacts. And I've put buildings in quotes there, because I think if we actually manage to do this, the buildings that we will be making, I think, will be so different to the buildings that we have now that they'll probably have a different name. So I've put buildings in quotes. But anyway, buildings that are beneficial and enriching to the environment, that do not degrade but perform better as they age, that are a pleasure to construct, and that are delightful to interact with. So again, that made me think in the same way I tried to think of existing examples of sustainability. I tried to think of existing examples of anything that was regenerative. Is there anything that humans do that is actually regenerative and beneficial? And not necessarily thinking about construction, the first example I came up with was an apple tree. So I'm lucky enough to have quite a large garden which has several apple trees, and every year these trees produce lots and lots of fruit. There's absolutely no external input. We don't give them fertilizer. We don't do anything. The trees just take nutrients from the ground, rain, sunlight, and make apples. There's no packaging, there's no transportation, there's no waste. We eat the apples, we just throw the cores back on the ground under the tree, and it grows. We get more and more apples each year. One day it will die, but by then more apple trees will have naturally grown around it. So it's actually certainly a self-sustaining system, but then it goes way beyond that. So that would maybe be sustainable, but actually that tree does so much more. So it stores carbon dioxide, it produces oxygen, it provides shade and cooling. You can sit under it on a hot summer's day. It intercepts rainwater to reduce runoff. It looks beautiful. It provides food and habitat for wildlife and mosses and fungi, and it provides a climbing frame for my children. So to me, that's regenerative. It's something that's self-sustaining, but also has a whole range of benefits. But we start to spot a theme here from my early days of engineering, where I felt that maybe trees would be better than a stainless steel sculpture, through to the responsive materials, and actually thinking that plants might work better as a responsive element on a building, through to looking for a regenerative example. And again, we find trees and living organisms. And there's always this feeling that actually the one thing on this planet that works in a regenerative manner is living organisms. And then when I look for examples of the built environment, although I think built is the wrong word, one example of what I think of as a regenerative, restorative example of a piece of infrastructure are these living root bridges in India, which you could well be familiar with. They're a really sort of classic example of this. And here I'm showing images from this fantastic book, Low Tech, Design by Radical Indigenism by Julia Watson, which gives a whole range of examples of people living sort of in harmony with nature and using nature and natural processes in beneficial ways in different contexts all over the world. And this example of the living root bridges, so to cross these rivers, which become very swollen rivers during the monsoon season, the people have woven the roots of the trees together across the river, and over decades created bridges that were strong enough to walk across. And of course, those bridges get stronger and stronger over time. So I think that's a really important concept, is that everything we build now is sort of at its best on day one, and then degrades. And we always have this process of degradation and either needing maintenance or things degrading and eventually failing. But here, using nature and using living organisms, this gets stronger and stronger over time. And over tens, hundreds of years, these bridges have become incredibly strong and resilient and able to cope with the floodwaters. So I found that a very inspiring example, which made me realize that I think living organisms are the key to creating a regenerative built environment. We've got examples that I've already shown across the top, but then there are plenty of others. On the bottom left, we've got reed beds being used to process sewage and clean water. We've got traditional microbial processes like composting. And on the right, we've got a green roof protecting the building, providing cooling, and also a habitat for insects. So there are lots and lots of these individual examples of using nature or other living organisms in a beneficial way for humans, but also at the same time benefiting wildlife and microbial life, and sort of enhancing ecosystems. But I think then even more interesting is whether we can look beyond those individual sort of plants and individual organisms. I think we always have a tendency to try and simplify things. I think the natural world is so complex that we always try, just going back to sort of take individual parts of it and make use of them, because that's what we can more easily understand. But actually, I think the real strength of the natural world is in its complexity. So here we've got a mixed woodland, which is a very complex, multifunctional, multi-scale, self-sustaining ecosystem. And when we put that next to a modern house, which is static, it has some very, very simple functions. It can't respond to the changing seasons or the changing weather. It's environmentally damaging when we make it, and then it degrades over time, and we can't reuse anything at end of life. It looks like a very bad way of doing things compared to these very rich natural systems. So about 5 years ago, myself and a few other colleagues in the School of Architecture at Newcastle and in the School of Applied Sciences in Northumbria University, we set up a research hub called the Hub for Biotechnology in the Built Environment. And when we say biotechnology, that's biotechnology very, very broadly, from sort of cutting edge engineered microbes, changing the DNA in bacteria to make them perform particular functions, sort of very high-tech biotech, all the way through to very traditional biological processes like composting, like use of natural materials and use of sort of nature-based solutions. So it's a very broad understanding of biotechnology. And what we were setting out to do across these 4 research themes was to create buildings that metabolize their own waste, so we can get circular flows of energy, materials, and water within buildings as we get within natural ecosystems. Buildings that are grown using living materials, either living engineered materials at the sort of high-tech end, or much more simple grown materials, but also buildings which modulate their microbiome. So through the design of the surfaces within the building and the ventilation systems in the building, can we have a healthy microbiome? Can we have healthy microbial life within the building? So not trying to make the building sterile, but actually having a healthy microbiome, so it's positively healthy simply to inhabit the building. And then to do all of that within, of course, an ethical, responsible framework, and to make sure that we take the fundamental science and scale it up and apply it at large scale. And I love this headline from a children's newspaper from when we set up the Hub for Biotechnology in the built environment: mushroom houses powered by poo, which was just a perfect description. I think we are looking at mushroom-based materials, and we are trying to power houses using human waste. So it's a really nice summary. And to do this, we set up various facilities at different scales, from labs to workshops to this experimental building, the Ohm, which was a place that we could experiment with these new technologies at large scale. It's very unfortunate that the Ohm is made with concrete, you can see there, and steel, and that's a whole nother story. I would have much preferred it not to use those materials. It was very difficult, a very difficult process, which I won't go into details now, but it's amazing how hard it is in the UK at the moment to do something that I thought would be simple, like build a timber building. But between the university and the contractors and all sorts of things, we ended up with some conventional construction materials, but we still had this building which we could use to experiment with these new biotechnologies. And so we have a self-contained studio apartment, sort of the home within the Ohm, this self-contained living space, and with shower room, and then a lab underneath, and all the waste from the studio and the toilet and the shower room feeds down into the lab, where we look at processing human waste, or waste from washing machine, and using microbial processes to process microplastics. And around this we have prototyping spaces, and on the outside of the building we can put materials on for sort of weathering testing and so on. And it's all made also for interacting with the public and showing people these new materials and new processes. So of course we got to work sort of filling this building with experimental prototypes, and I want to just talk you through some of those prototypes, which I think might be sort of small tentative steps towards regenerative architecture. Definitely not remotely there yet, but I think there's some very interesting materials and processes which we've been working with. So the first one is bacterial cellulose. So this is a material which which we can grow in sheets. We use a bacteria which eats sugar and produces cellulose, so the same fiber that wood is made out of, but in this case it's just pure, it's a mat of pure cellulose fibers, which is grown on nutrient-rich water, so essentially sugar and water, and it needs oxygen as well, so it grows in a flat sheet, and we get this material which is strong, flexible, compostable at end of life, and we've worked out how to grow it in non-sterile conditions, because a lot of these materials tend to be normally grown in very controlled laboratory conditions, which isn't very practical if we're trying to scale up and use these materials at building scale. So we're also looking at, can we make these materials, in a normal sort of workshop or factory rather than in a lab. The one problem with bacterial cellulose is that it does need sugar to grow, which isn't ideal. We don't want to divert sugar that could be eaten into production of construction materials, but we're looking at using industrial waste. So for example, the waste from sugar beet processing has sugar in, and potentially can be used where it couldn't be used for food. So that's the important thing that needs addressing here. But just moving on, so here you can see the bacterial cellulose, growing in these trays. These were about sort of 60 centimeters by 30 centimeters. So we're growing these quite big sheets of bacterial cellulose. It needs to be quite warm, about 25 degrees. We do that by having a south-facing glazed facade and trying to do most of our growing in the summer, so we're not having to heat the space and use a lot of energy to heat it. It takes about 2 weeks to grow a sheet of the material, but it doesn't need light, so you can cover these and stack them up, and as long as there's some ventilation, it will grow in the dark. So that's quite nice. It doesn't need to be laid out like that. That's just for the photo. And then we can harvest these sheets, and when they're wet, they're very thick. They hold a lot of water. But then, and first thing we did was just try them as a sort of cladding system on the outside of the building. You know, it's a new material. Let's see what it does. So we had these steel wires. You know, they could have been timber battens, but they were steel wires, and we just folded the sheets of cellulose over the wires. And this is when it's just been harvested, and it's wet and thick. It smells a bit strange, and we got a lot of negative feedback at this stage about why are we hanging pig skin on the outside of the building, and it did look quite disgusting. But as it dries, the material becomes much thinner. It becomes kind of leather-like, and the thing we didn't expect but was very, very helpful was the material actually stuck to itself really, really quite well. So all these different layers, sort of shingles, stuck to each other and formed this waterproof cladding, which has now been on the building for about 2 years. It's still there. I mean, we thought it might just be ripped off in the first storm, and then we'd, you know, go back and do more development. But it's incredibly strong. It's coped with freezing and strong winds and rain. And the rain doesn't get through. It makes a really nice sort of waterproof cladding. The only problem now, after about 2 years, is we're starting to get some sort of black mold growing on the surface. So we're looking at different strains of bacteria that make bacterial cellulose, which is more water resistant, or also putting some oil on the surface. So putting a natural oil, linseed oil, on the surface, as you would with timber, just to make it a bit more water resistant. But as a kind of early stage quick prototype, it was very, very interesting to find this material worked, and that potentially it can be grown on site, very minimal input, if we find a source of sugar that we can use, and then we grow this material. And as the material is so sort of cheap and easy to grow, if these shingles do need replacing every so often, it would be easy enough to grow some more and, you know, have a sort of process of replacement. Just moving on to some other work in the OHM, other projects. This project, Biomateriome, really had two purposes. One was to show all these new materials to the public, because after that response to the bacterial cellulose, people thinking it was pig skin, we wanted to invite people in to interact with the materials, but then also being interested in the interaction of the materials and microbial life within the building. So I'll just skip. So one thing was to create this material library where people could come and interact with a whole range of new biomaterials, very unfamiliar materials, and start to understand people's reactions to those materials. And then the second part was installing samples of a wide range of materials in the studio apartment, and then taking samples from the surfaces of those materials, taking swabs, and then extracting DNA sequencing, and understanding the microbiome and what was living on those materials. And this has been carried out for, I think, the last 2 years, looking at the development of the microbial communities on those surfaces, and then looking at events. For example, if we have a gathering, we have a meeting in the apartment, or we have a party in there, and there are lots and lots of people in there, what happens? Do particular surfaces stay sterile? Do particular surfaces have an increase in certain microbes which might be considered healthy? And what we're aiming for is something like live yogurt or other fermented foods, where we get these positive, healthy bacteria living on the surfaces within the building. And we also look at different ventilation strategies. If we've got mechanical ventilation, or if we're allowing fresh air in through the window, again, how does that change the microbial life? And we don't quite have the results yet. It will be published soon. There were vast amounts of data, and now it's the complex process of trying to work out the sort of correlation between different materials and what's living there, and which ones are potentially beneficial. Something else we've been doing, as well as looking at particular materials, is looking at the flows of water and energy and materials through a building. And so this is how things normally work in a home, where we have a lot of inputs: mains, treated water, food, packaging, energy. We have a few simple processes within the home, and we have a lot of damaging outputs: food waste, packaging, sewage, greenhouse gases. So that's the normal kind of linear operation of a home. And we were trying to think, how can we close these loops? How could we have a self-sustaining home? And we're trying to do it on the scale of a single house, but realistically it might be better to do it at the scale of a community. But we were sort of challenging ourselves to try and think about circular systems within an individual home. And so, sorry if the writing's a bit small, but what we did initially was to think the sort of most vital resource within a home is the human waste. So we wanted to make the best use that we could of human waste. And it seems a shame that we normally just flush our waste down the toilet and send it off to the sewage treatment plant, where either it's not used beneficially, or where anaerobic digestion produces gas, and perhaps farmers use the solids on their fields, but we've paid to get rid of this resource. So couldn't we use it within our homes beneficially? So the first thing was, actually it's very useful to separate the solid and the liquid waste. And we found this fantastic prototype toilet, which looks exactly like a normal toilet, but separates solid and liquid waste. And so the solids go down one pipe into an anaerobic digester, small anaerobic digester, which produces gas from the solid waste, and also leaves the solids behind, what's called digestate, which can then be used for other processes. And then the urine from the toilet goes down another pipe into a microbial fuel cell, which uses a microbial process to produce small amounts of electricity. I'm not sure on the detail, that's not my area of expertise, but we get these very small amounts of electricity, which need some rethinking, because we're used to using very large quantities of electricity, and this gives you sort of millivolts. And they're interesting questions about how we could make efficient enough electronics to make good use of the electricity from the microbial fuel cells. And within all of this, we collect rainwater, which runs the toilet, but also we can recycle the water back from the microbial fuel cells, in fact from the anaerobic digester, and so we keep the water in a closed loop. So this was kind of the core of the idea. But then we've still got this digestate coming out. We've still got lots of inputs and outputs, like food and so on. So we then tried to expand this. I'll zoom in a minute. So we've still got those sort of core technologies in the middle, but then how do we use the digestate, the solid waste that's left? we can use that to grow things. We can use it to grow biomaterials if we're needing more construction materials, we're needing to repair our building, or we can use it to grow food. And that could be, if we have space, we could be growing food outside, or this digestate could be used as nutrients for vertical growing systems, sort of high-tech, intensive urban agriculture within buildings. So we can be growing food or biomaterials. Of course, that we need to prepare that food, and if we've got very small amounts of energy from the gas or the electricity from these processes, we don't want to be using sort of modern cooking techniques which use a lot of energy, running an oven or boiling water. So again, we can look to biological processes, traditional food preparation methods like fermentation, or maybe slow cooking, which use much less energy. And then that feeds into consumption, obviously, back into the toilet, and we end up with more of a closed loop. I mean, of course, it can be difficult to grow enough food, and what we're doing at the moment is trying to quantify all of these processes to understand, how much food can we grow, how much energy can we make, how much external input are we going to need, or what else do we need to supplement this this process to actually make it circular, and is there anything left over so it can actually be regenerative? If we have excess fertilizer and digestate, can we then use that to start restoring natural areas, for example? And then my last example is about going back to materials, is about using mycelium as a construction material, which you've probably all heard about. This it's become very popular over the last few years to use mycelium in various different forms. So mycelium, which is essentially the roots of mushrooms, so it's the very extensive network of roots, mushroom roots, which grow under the ground in forests and form these incredible networks in forests, which sort of share nutrients, and people think now sort of communicate through the forest and share resources between trees and do some incredible things. But these roots will also bond together loose materials. And it's often the challenge in construction is trying to find something that will bond together small materials. That's why cement is so useful, because it bonds together gravel and aggregates. But mycelium roots also do a very good job of bonding together materials. And so if we grow mycelium through any cellulose-based waste materials, so it could be sort of sawdust, wood chip, waste paper, coffee grounds work very well, other food waste, they're bonded together. The mycelium partially uses those materials as food, but it also bonds them together into a rigid material. You don't need any other input. That's the great thing here. We don't need sugar. We don't need other nutrients. We just need the cellulose from the waste materials. And then it's got some fantastic properties. It's got reasonable strength and stiffness, but also good insulation, good acoustic properties, very good acoustic insulation, and is also fire resistant. So a lot of good properties there as a construction material. And then at end of life, it can be composted. What we found interesting was that a lot of examples of people using mycelium, and this example, the Hi-Fi Pavilion in New York, which was a great project to really get mycelium being better known, very high profile project, but it just used very simple sort of bricks. So, we can grow mycelium in molds and make bricks. That seemed like a wasted opportunity when we have this material which can be formed into any shape. It can be grown on site, all sorts of different ways. So it seemed strange to just make bricks as you would with other materials. Another example on the right this is a company that's trying to commercialize mycelium biome, making these insulation panels, which makes sense. It's fantastic material, but again, just making these flat rectangular panels seemed like, in terms of sort of architectural creativity, perhaps a wasted opportunity to just hide these panels within the wall. And what we wanted to do is really celebrate the material and look at its potential for building in new ways. So we had the opportunity to create a large installation for the opening of a gallery called the Farrell Centre in Newcastle, which is a new architectural gallery. And they're having their opening exhibition was called More with Less: Reimagining Architecture for a Changing World, which we thought was perfect for trying to do something with these materials. And we created an installation called The Living Room. And it started with us questioning why we live in sort of square, hard boxes, and why do we line those boxes with plasterboard, as we've said, very environmentally damaging. Walls can't breathe, can't be reused or recycled. So, why are we building like this? And so what we set out to do is think about how we could build and live very, very differently, with minimal environmental impact, or possibly positive environmental impact. We use locally grown materials or waste, make something that's compostable at end of life. We use those materials to make complex, soft, curved spaces that feel sort of cozy and safe. We make the walls breathable, and so they can store moisture, moderate humidity, and we make those walls bioreceptive, so they have a healthy microbiome. We didn't quite manage all of that in this project, but we did certainly the first steps. So the first thing was to find genuinely waste material, because a lot of people make mycelium materials using sort of agricultural waste, but actually, is it waste, or did it have a good, or did the farm actually have something it would do with that waste? Plow it back into the land, use it as a nutrient for the next crop. So we spent some time trying to actually find cellulose-based waste materials. And over on the left, we've got sawdust from a small local sawmill processing hardwood. And this is a genuine waste material. They have some people who use the sawdust, but they make too much, and just have to dispose of it, leave it to rot away. The middle image is waste pulp from paper making. So again, a local paper mill, and they try and reuse everything as much as they can, but at the end of the production line, they have this pulp with very, very short fibers, which can't be used in any kind of paper or cardboard. And they spread it on fields to rot away, but it's of no benefit. So they have to pay the farmers to be allowed to spread it on the fields. So it's a genuine waste product. And the other things we wanted to create sort of the formwork and the form of this installation, we wanted to use waste materials, and I was working with a textile designer, and so we wanted to use wool, and we found that in the north of England there's an enormous amount of waste wool. So there are a lot of sheep for people to eat lamb, but the fleeces are quite low grade wool, and it's not worth the cost of processing them, and so the fleeces of the sheep are just thrown back on the fields and rot away. So again, it was a genuine waste resource. So we'd found these genuine waste materials, and all quite local. And so we then tried to develop a construction system around those materials: wool and sawdust, paper pulp, and mycelium. And so for the form of this of the living room, we used knitted structures, and the way that a knitted form will naturally create these complex curved forms. and then taking that through to computer simulation. And the idea was to have this enclosed, sort of cozy enclosed space, but then with lots of openings, lots of quite small openings, so children could sort of have fun weaving in and out, and then have one larger opening for adults to get into this internal space. And then, because we were working with this quite coarse wool, which can't be used for normal knitting processes, my colleague Jane knitted the canopy, the formwork that we'd use to form the shape of this structure, literally knitted it by hand using these thick bundles of wool, so not twisted into yarns, just bundles of wool, very, very sort of simple before they've been spun into yarn, and then literally knitting them by hand into a large canopy. So then inside the gallery, so we're going to make this installation as a single piece within the gallery. It's going to be 4 meters diameter by 2 meters high, so it gives a sort of reasonable space inside. So it had to be made in the gallery. And we set up this scaffolding frame, very conventional way of building using scaffolding, but of course it's completely reusable and very easily available. So we've got the scaffolders to come in and set up this frame, and then in the bag in the middle is the knitted canopy that will provide the formwork for the construction. And so this knitted canopy, about 70 kilograms of wool, was pulled up into position. There's a reusable metal ring in there, so we can pull the center up into position, and then we can start tensioning the knitted canopy into position and pulling it out. And the great thing about this, with the flexibility of the wool, is that we didn't have to completely decide on the shape before we started. Normally, with construction, every detail is decided, and then you just build it. Whereas here, we could really play around with the form during construction, and in response to the room, we could, pull and tweak and change the structure. So this is pulling one of the openings much higher to give the entrance for adults, and then making the others lower. And it was a really quite different way of thinking about construction, to have something that could really be adapted and shaped as it was made. And so this was almost ready. Still needs a bit of tensioning, but pulled out into this shape. So this is 4 meters wide and 2 meters high, really quite large scale. Then we needed to mix up a lot of mycelium paste. So we have mycelium spawn, essentially the kind of seeds of the mycelium, to get the process started. And you pre-grow the mycelium with sawdust for a while to get the mycelium growing in perfect conditions, because of course we were going to have to grow the mycelium in the gallery. Normally you grow mycelium ideally in a growing room, which you keep at about 27 degrees, nice and moist and dark. And we were going to have to try and replicate those conditions in the gallery, but we wanted it to grow as well as possible. So we sort of started it growing in the sawdust in controlled conditions, and then took it to the gallery, mixed it with the more sawdust and the waste paper pulp, mixed about 500 kilograms of pulp, but it's actually quite a light structure in the end, because it's 75% water. So as it dries, it becomes much lighter. And then we plastered the mycelium paste onto the knitted structure. So literally by hand. So it's like a very traditional kind of bit like applying mud to sort of traditional buildings by hand, and just smearing it on. And here we have a view down on the whole structure, completely covered in the mycelium paste. Then we had to seal it all up, because it has to be dark. If it's not dark, you get mushrooms produced. If you just want the roots to grow, which would naturally grow underground, it needs to be dark, it needs to be warm. So there is some energy implication there, depending where you are in the world. You want conditions of sort of 25, 27 degrees. Unfortunately, the timing meant we had to do this in the winter, so we needed a lot of heating in the space, which was very unfortunate. If we could have done this in the summer, then we could have had those conditions naturally and had much less energy use. And we just water it regularly to keep it moist, to keep the right conditions for the mycelium to grow. And it was left like this for about 2 weeks for the mycelium to grow through and to bond into the wool underneath. And of course, the great thing is the wool can also be, to an extent, can be digested by the mycelium, and so you get a very good bond into the wool. After 2 weeks of growing and then unwrapping and allowing it to dry for 2 weeks, and then the scaffolding was, well, the supports were removed, which was a very worrying moment of taking away all the supports, but we were left with this self-supporting structure. Then the scaffolding was removed, and we end up with this this finished installation. So really large-scale organic mycelium and wool structure. And this is what I meant about not describing the future of buildings as buildings, because here we've ended up with something so different. I don't think you'd call it a building. It's really quite unfamiliar and probably needs a new word. And of course, we weren't suggesting that this was, something that people would live in. We were really just trying to demonstrate how these materials, local waste, and living organisms could be used to make a substantial structure with very, very minimal input. Just looking at a detail, you get this fantastic texture. And when we saw members of the public looking at this was on public display for about 6 months. Had a lot of visitors, and people were absolutely fascinated by these textures and the two, the soft wool and then the quite hard mycelium, but with a textured surface and really complex colors. And people were really interested, and the contrast with the white box of the gallery we were in was, really strong contrast. Then just looking at a little cross section through the material, you can see how the mycelium has grown through the wood chip. Not everywhere. There's some little pockets where the mycelium hasn't grown so well, but generally the mycelium's grown through, and then it's all bonded into the wool, and it makes a really quite strong composite material. And we've done mechanical testing, and having the wool there makes the overall material a lot stronger. The wool fibers stop the mycelium material from cracking and makes it stronger in bending. So it all works well together, as well, of course, as the wool, providing the kind of permanent formwork. And then this was the inside, which ended up a little smaller than planned. The wool did stretch a lot more than we'd anticipated, so it ended up sort of sagging, and the inside space was a bit smaller than we'd hoped for. But again, it was very interesting seeing people coming into this space, a really very different space to what anyone's used to, but incredibly sort of cozy and soft, and also a very, very quiet space. The combination of the wool and the mycelium had an amazing acoustic effect that you couldn't hear anything outside, or it was very, very muffled, and it gave this really sort of calm, quiet space. So again, it was very interesting seeing members of the public experiencing that, and sort of thinking about how spaces can be very, very different. And it got a very good reception from the press in the UK and beyond. And we were pleased because people could very easily have just thought it looked unrealistic and not like a practical building, but I think people accepted it as a kind of sculptural exploration of new ways of building, and seemed to get quite excited about the potential, which takes me back to my original question about, about whether we can go beyond sustainability and create these positive buildings with positive impacts. I think this is just, it's a tiny step in the right direction. But again, the problem here, I think this approach we used here is getting quite close to sustainable, but not so close to regenerative, because it's just looking at one material or two materials and one system. And I think to get that regenerative element, we need to go back to the processes I was looking at with the using human waste and so on. And it's those kind of cycles of materials and energy and water and sunlight. And it's starting to use those cycles alongside a whole range of different living organisms of different scales, from the bacteria we have and the fungus we have working here, the bacteria that make bacteriocellulose, through to much larger scale natural systems and trees. And when we start to get all of those working together, I think that's where we have scope to make something regenerative. But it really involves that bigger systems thinking. We have recently published a book about our work in the Hub for Biotechnology in the built environment. So please look this up if you're wanting more. Bioprotopia, designing the built environment with living organisms. And that brings me to the end. Thank you very much for listening, and I'd be very happy to answer any questions.
Thank you very much. Okay. Thank you very much for your talk, Ben. Can you hear me?
Yep, I can hear you. Yeah. Are there any questions there?
Okay, now I cannot hear you anymore.
Oh.
We have a few questions from the lecture hall. Obviously, you can hear me, but we cannot hear you.
Right. Can you hear me now? Or?
Yes, I have to turn on the sound. Thank you. It needs a village, right, to do things. One is not enough.
Can you hear me? Can you hear me?
Okay.
Still not hearing.
Pardon?
We can still not hear him. Just said something that was still not. I believe it's really in the Steam settings. So
I get some help, and I think this is also the first question for you then.
it should be right on the speaker.
Sorry, I didn't hear the question. Or
One moment. Ben?
Yep.
Yes, we hear you now.
Yeah, sorry, I didn't hear the question.
Perfect. Yes, there was no question yet.
Okay.
But maybe the easiest one if you come here, right, for the question.
So, hello, first of all, thank you for the really interesting talk. I have actually two questions. The first one is more on the product side, and the second one more on the architectural side of things. So for the first question, when you were showing the home concept and we're talking about the toilet, it might sound like a very specific or like in-depth question. So I'm more wondering generally. Obviously, you said it kind of like has the solid waste and the non-solid human waste components. But for example, what happens to the bacteria stuff, like if you're sick and then your normally solid waste also becomes non-solid, which obviously is a problem that might occur.
Yeah. I don't think that causes a problem. I think the process is robust enough to cope. I mean, the way it separates the solid and the liquid is to do with, as you're sitting on the toilet, and the liquid by surface sort of hits the front side of the toilet, and through surface tension is taken down one pipe, and then the solid just drops in at the back and is flushed as usual. So even if the solid is liquid, it'll end up in the right place, and then the process is robust enough to cope with that. The important thing, what's interesting about that toilet, is it works exactly like a normal toilet, because previous separating toilets were a bit different. They often maybe were dry, like some composting toilets are, and you get more smell. It's just a bit unfamiliar, and people are generally very unaccepting of any changes in toilets. So it was great that this Swiss company Laufen made this prototype toilet with basically no market, because nobody needs those toilets at the moment, but to promote research into separating toilets and localized waste processing, so they would then sort of be ahead of the game when that's needed, which was really quite forward thinking of them. So it's interesting. And second question.
Yeah, the second question is about the mycelium, and I was wondering, especially if you have like this woolen structure now, and we would say it's more like on the outside, and there's obviously all the elements coming, like wind and snow and like all throughout the year, the sun and stuff. How long-lived really is this kind of structure? Are there any more additional things needed, coatings needed maybe to make it more resistant to the forces of surrounding?
Yeah, no, good question. So I mean, that was, the living room was designed as an internal installation, to be used in the gallery, and we were thinking that a system like that could be used internally in buildings as kind of internal walls, or particularly if we were sort of retrofitting a building and changing the internal spaces. But it's definitely what we'd like to do next, is make something that can actually be outside, but you'd need another layer, because the mycelium is not waterproof. It's kind of water resistant for a bit, but it will absorb water, it will get heavy, it will lose its strength. Also, if it gets wet, it will start growing, so you'll get mushrooms growing. And it's something I forgot to mention, because normally if you make small scale mycelium objects, you usually put them in an oven to dry them, but also to kill the mycelium, so they're inert. But of course, we couldn't put it in an oven because it was so large. But that's actually quite interesting, because it's dry, so it stops growing, but the mycelium is still alive. It's just dormant, which means it can come back to life, which could be a problem outside, because it will start growing mushrooms, but actually can be very useful, because then if there's a crack, then you can just add water, it will come back to life, and it will grow back together. So that idea of making structures that are able to get stronger with time, or able to self-heal, it definitely addresses that. So to use it outside, we need a waterproof coating. And the obvious thing is the bacterial cellulose, which could make a waterproof coating on the outside. So we could have bacterial cellulose, then mycelium, then wool potentially, or anything else to form the shape. They could work well together.
All right, thank you very much.
Do we have another question? Yes. You want to come here? It's probably easier, or easier to understand.
My question in the chat, but I can't find it anymore. Hey, yo, thank you also for the presentation. It was very interesting. My first question was, in the beginning, you mentioned that you were talking about timber as a wood structure and as a sustainability way to in comparison to steel or concrete. And you said that monocultural forests are one of the disadvantages when it comes to producing timber. But this was a question I was already wondering for a couple of months now. Why is it such a disadvantage? Of course, I can imagine that it's better to have like mixed cultures of mixed forest cultures. But when it comes to the comparison to concrete or steel, I think why is it still a disadvantage to have monocultural forests?
Yeah, I mean, so in comparison to steel and concrete, I think it's still enormously beneficial. There have been a lot of concerns recently about the amount of wood that is needed, particularly if we move towards using big slabs of cross-laminated timber, which initially was thought of, or is currently thought of as it's good. We use a huge amount of wood in the building, so we're storing a lot of CO2 in the building, we're locking it away. But then there are concerns about availability of that much wood. It takes a very long time to grow a new forest. And if there is this pressure to grow more and more wood, then the problem is, are we cutting down existing biodiverse forests and plant these plantations, which I know has been happening in Scandinavia. As there's this demand, they can see the demand for wood is increasing, and so it's a question of destroying existing ecosystems to then grow timber. I mean, it's happened in the UK, in the north of England. There's some very large forests, pine forests, used to produce wood for construction, and they were grown on peat bogs. So these bogs which store huge amounts of CO2 and have very unique flowers and wildlife, and those bogs were drained so they could then plant the pine trees, and people are realizing that destroyed those habitats and released large amounts of carbon dioxide. And now in some areas they're cutting down the pine forest, they're sort of blocking up the drainage and allowing the peat bogs to fill with water again and trying to restore those ecosystems. So I think a lot of damage was done in destroying natural environments to grow the timber. But at least once you have got the forest, monocultural forest, I don't think it's harmful in itself. I think it's just of what might have been destroyed to grow it.
Yeah, thanks. And another question to the mycelium, because you also showed this one project where they were staking like the bricks. And I heard you, like, in one sentence you said this is like a missed opportunity because it is a better, or you prefer a better way when it's like in organic form or something. But don't you see also potential in replacing like traditional bricks now with sustainability bricks made out of the mycelium?
Yes. Yeah. No, I mean, obviously it's still a good thing to do, and if you can replace existing insulation with insulation panels made out of mycelium, and so on. I think particularly it's a shame to not make full use of all of its properties. What I'm thinking of, for example, the surface of mycelium is a really interesting texture and pattern. But if you're just sticking to the traditional way of doing things and you just hide it away within the wall, if you're just using it as insulation or maybe as somewhat structural infill, and then you still line that wall with plasterboard and plaster, and all the other layers that you normally get in a modern building. And that's a shame because you're then using these destructive materials. I think it's good to try and use that material as much as possible, and if it can be the internal lining of the wall and it's providing insulation, and then if it is exposed, you'll find that you'll get the benefit of the fact that it can store moisture and regulate the humidity in the building, and the building can breathe, and we start to get sort of lots of benefits. Whereas if we just try and replace a single material within the wall build-up, you might lose some of those benefits. So apart from the kind of creative side of thinking we could build differently with it, I think it's just a question of trying to use it to replace as many materials as possible. Maximum benefit.
Okay, good. Yeah, thank you very much.
So I have a question of those materials, such as the cellulose production and how to cultivate the mycelium. And I was thinking about downsides of those materials because we have heard a lot of positive sides. And obviously, it's the extensive cultivation of those materials. And do you think when we overcome the time of to produce the cellulose, which takes like 2 weeks, do you think when it's would be faster, there's like a more like a breakthrough of those materials and using in architecture to experiment more, to develop faster, to incorporate in architecture? And for example, with the bacterial cellulose to program the genetics that they produce faster, or more positive effects?
Yeah.
Like-
So yeah. So certainly, we haven't so much been thinking about the speed. My colleagues are working on modifying the properties, particularly making it more water resistant. So changing the genetics to make it more waterproof, which would really help the durability of the cladding. Also, I think to make it more fire retardant as well as a cladding material. So it is really exciting that you can modify the genetics and change all of these properties, which I think in time will have a big impact. We hadn't really been thinking about the speed so much, but I suppose in a commercial setting, there is always a problem if you try to scale up the process and it takes 2 weeks to grow. It's interesting whether, if you're growing in a factory, you need to speed that up. Otherwise, you just have huge rooms of growing space. But it's whether if you grow it on site, then you can kind of fit it around other activities and it can just sit there on site for a couple of weeks. And then it might not be such a problem, because actually, if you pour concrete, you have to wait, a week or two for it to gain strength anyway. On a construction site, things tend to take some time, but it certainly would be good to speed it up for sort of commercial production in a factory.
Thank you.
One more question coming.
Yeah, I got the question about the emissions. We've always heard that building and material sector is about 40% of the emissions worldwide. But do you think it's actually possible to reduce that? Because we're pushing to reduce emissions in all of those sectors constantly. So maybe it's just given that building and materials just takes up a lot of those emissions.
I mean, it might keep proportionally, it might stay the same if everything's being reduced, but of course, if you can make big reductions in the overall total, then the proportions don't matter so much. I mean, I think what's important is to try and make some big step changes, because I always see these small changes which never seem to add up to that much, particularly as there's more and more construction going on. Of course, the first thing is to build less. The whole idea of reusing existing buildings, but then I think there's potential for these biomaterials in retrofit and in working on existing buildings. And I mean, it's one of the interesting properties of mycelium is that it can bond to wood. It will grow into wood slightly, and so if you're working with, for example, an existing structure, trying to add insulation or extend the structure, and to have a material which you could grow in situ, a bit like if you're casting a concrete wall, but you could be growing mycelium, and then it can bond into the existing timber structure, for example. I mean, it all depends on the exact application, but I think retrofit's very important. But then if we can really make a step change in and massively reduce the use of steel and concrete, and I think they'll always be necessary. For example, foundations are very difficult to there aren't good alternatives to concrete for foundations, but if we're making very light buildings, perhaps with timber, possibly with biomaterials or natural insulation materials, you can have a very, very light form of construction. So you should then be able to have much smaller foundations. So you might have half as much concrete in the foundation and very, very minimal impact materials in the structure. and then you've made a big difference.
Hey, I just had one question, which was just coming up before that one. Is it like we're also talking about recycling materials after we rebuild buildings because they're not fitting into anything anymore? Is this also possible with the recycling? Like as you were talking about, it's connecting with the wood. So how can you reconnect it if they are like together?
Yeah. I mean, I think the idea with the mycelium and the bacterial cellulose is that you would compost them or you'd use them as food for growing a new material, I think, rather than reusing them. I mean, it would be possible to reuse them, but I mean, generally, they're not going to be as durable as, you know, as a brick or a steel beam, you know, which I think have much more scope for reuse over and over. Whereas I think with these materials, it's more realistic that you'd break them down either through composting or as food for growing a new material. But again, I think it's important to think about doing this locally. I think one of the big problems with, you know, for example, recycling steel and it's transported to some big processing plant and there's a lot of energy. And so while steel is recycled very well, you've still got enormous amounts of energy. But the processes we're talking about here of composting or just allowing material to be used to grow new materials could be done very locally with very little energy or transport, which I think is important.
Thank you.
Okay, thank you very much, all of you. I will skip now to the questions from the students that are in the Zoom meeting. I would go through the questions, but also let the students ask them themselves. So I skip mine. Maybe at the end I have time because we have 10 minutes left. There is a question from iPhone. Okay, that was yours. So then we have a question from Daniel.
Yeah. No, my question was, is it
Okay.
possible to grow these bacterial cellulose in different forms and then sheets? Maybe in other casting models?
Yeah, it's a good question. Because the bacterial cellulose grows at the interface between the water and the nutrients and the oxygen in the air. So it tends to grow as a flat sheet on the surface of a liquid. But we have been experimenting because, of course, it would be very useful to be able to grow different forms. And one of my PhD students has been trying to do this for the last 3 years by bubbling water, by bubbling air through the water and sugar through the nutrient bath to try to get the bacterial cellulose to grow in 3-dimensional shapes. And she's had some success sort of growing streamers and all sorts of interesting shapes, but they've tended to be very, very weak. It's quite difficult to control the flow of air through the liquid well enough that you get a kind of thick growth. But there's possibility there. So, you know, it's very early days. So if we find good ways to control sort of where the air is and where the liquid is, you could then grow, you know, some really interesting forms, which I'm not sure. I think for sort of large scale architectural uses, actually having flat sheets is quite useful. And when it's wet, they're very, very flexible. So they don't have to stay flat. So if we're trying to clad a sort of complex curved structure, it works really well. You can bend them and then they stick to each other. But I think maybe for smaller applications, sort of product design type applications or packaging, which bacterial cellulose is popular for, it could be very interesting to be able to grow it into more complex shapes.
Thank you.
Thank you, Eric.
Yeah. So my question is if either the cellulose or the mycelium has potential to really replace concrete in the building. Like is one of these materials has the possibility to have static use instead of concrete and steel? And you think it's just like in a large scale, small scale?
No, I don't think they can completely replace them because structurally they're just not as strong. So I think they work very well with timber construction. So I think a combination of using timber structurally and perhaps not big slabs of cross-laminated timber, but a sort of stick timber structure, and then you could use mycelium or other materials as the kind of wall structure. But there also, there are other good materials like sheep's wool insulation, for example, and then perhaps mycelium as an external waterproofing layer. So no, I'm definitely not saying mycelium and bacterial cellulose will replace everything and the whole future of construction. We're kind of exploring some materials to see what we can do with very low environmental impact. But I definitely think wood will be part of the equation.
Okay, and maybe another question. If you talked about this thing that mycelium can grow in future, like, do you think it could be possible to have like a building which can extend just with like feeding the mycelium, or is it like that the mycelium needs like 2 years to grow? Like how long is the process to grow for the mycelium?
Well, so it takes about sort of 10 days or 2 weeks to grow when we make a piece or a structure, but that's with some mycelium already sort of everywhere throughout the structure, and then it all grows together. If you were trying to start with the mycelium in a building and then expecting it to grow a long way through some new materials, it would take longer. So you really need to sort of seed the new structure with mycelium. I think it's more useful that it can repair cracks, which is very, very useful, and the fact that you could just spray it with water and it will repair the cracks. And in fact, we have researchers working on another self-healing technology, which I didn't mention, of using microbial self-healing in concrete, but also in stone and in earth construction. So I think the ability of bacteria to just sit dormant until they get wet, until water comes into a crack, which happens naturally if the outside of a building's cracked, water comes in and then they can come alive and repair the crack. I think it's really exciting across all sorts of different construction materials.
Thank you very much. We are almost at the end. I have to ask you a last question, please, because I liked very much your slide where you explained the apple tree story of life. And it reminded me to Newton, because he watched, he watched the apple and then he had this great discovery. And what we have heard today is, first of all, a number of innovative materials, innovative experimental approaches. But what I like most also for our students is that by looking at these things, you come back to the basic of life, to the basic of building. What is architecture? What's the role of the architect? Where are we living? And so my last question is maybe where you can round it up. Do you see the apple tree as a paradigm for this new future architectural approach?
Yes. The simple answer is yes. No, I mean, that's to me, that is also the most interesting part. And whether it's the apple tree or the other trees, I seem to always come back to trees in any problem. I always seem to come back to trees and that they just have so many benefits, and that it's so complex the way they function, but that they do so many useful things. And it's interesting, they do so many useful things for people, because actually there's no reason that they should necessarily be useful to people, but this way that they provide shade and cool cities and stop flooding and provide materials and produce oxygen, and it's as if they've been set up to do about 10 different things to help people, and yet we then make our buildings which are designed to help people, and they do far fewer useful things for people. So I definitely think, whenever you're designing something, if you think of a tree and think of that as your kind of gold standard of how well something can perform, and then look at the thing you're designing and realize how rubbish it is, and try and do better and make something that has many benefits and very few or no problems. And it's very difficult, and that's why I call all these developments just tiny little steps, because then we compare the mycelium to the tree, and we it's quite unimpressive, and really not very good. And again, we have to go back and look at the tree and go, yeah, that's how we should be designing. So yeah, definitely that's the future, hopefully.
Thank you for this almost final word, because we have a very urgent question, a very urgent last question, please.
Hi. So sorry for the third question now. We all know that for something to be really adopted by the people, they have to kind of like it or see something in it to actually want to adopt it as well. So there might sometimes be very many like small things which they feel like, okay, this is not what I want, or this is not what I like, and then they will not give it a shot at all. So the question arose while talking to a colleague that is there like a specific smell, for example, to mycelium? So if you use it like, in rooms, and then the rooms smell like the forest, and for some people it might be something good, but for some other people it might be like, I don't want this ever, or something. So how would you say is this?
Yeah, no, that's really good question. The mycelium itself actually has very little smell, or quite a very subtle smell, which I think probably has most scope for being a positive thing, because it's just a very subtle, sort of very hard to describe smell, but very much not offensive and not too strong. And the way we were using mycelium with wool, the wool had a much stronger smell of sheep, which was definitely what people were responding to. And again, some people like it, some people don't. It's the bacterial cellulose has a very strong smell. Partly we use vinegar as part of the medium that it's grown on, to change the pH. It's a big challenge is avoiding other organisms and other molds growing, so we try and sort of use fairly natural additives to optimize the conditions for that particular bacteria. So there's quite a strong vinegary smell, but then also bacterial cellulose just has its own quite distinctive, strong smell. So again, using it outside might be okay. If you're trying to use that internally, I think that would be very challenging. But it's just very interesting of whether people will start to accept these things, because actually the materials we use at the moment in buildings, we use silicon sealant, which has a horrific smell and is probably very bad for you, and a lot of paints give off horrible chemicals for a few days and things. And actually we use really unpleasant materials in our buildings that are bad for us. These materials smell interesting, but aren't harmful, and they're much better for us. So I think it'll be a slow transition, but yeah, it's a very interesting question.
Thank you very much. And once again, sorry to bother you again.
Thank you very much, Ben. Have a great day, and hope to meet you again.
Yep, definitely. Thank you very much.
Good luck for your projects. They are fabulous. Thank you for introducing
them. Thank you. Thanks, everyone.